Hello everyone, my name is Francesco and today we are very excited to show you our research on fine-tuning large language models for automated subjective objective assessment and plan note generation within medical contexts. Now here's a brief outline of our presentation. We'll begin with the problem our research aims to address, followed by the methodology we used and the results we obtained, and finally we'll wrap up with the key conclusions from this study. Now, as we know, artificial intelligence is one of the most transformative technologies that we have today, with real-world applications across many industries. In the healthcare industry itself, it's already assisting doctors in reading medical images such as x-rays and helping detect issues like tumors more quickly. However, even with all these advancements, AI still isn't fully independent, with many tasks still requiring human expertise and human inputs, such as identifying abnormal cells. But one area where AI can bring immediate value is in documentation. Doctors these days spend hours every day documenting and writing notes, and we believe that AI can ease their burden by automating this process, which is why in this paper, we mainly focus on training large language models to summarize the SOAP notes from a given dialogue between a doctor and a patient. Now, like I've said, currently, doctors spend a significant amount of their time documenting and writing SOAP notes, which will be then used to generate the electrical health records for each patient. A recent study found that doctors typically spend 45% of their time on documentation alone, and this can lead to fatigue, burnouts, and even less time for patient care. So before diving deeper into our work, let me first explain what SOAP notes are, since they're pretty much central to our research. SOAP is a structured format that doctors use to document patient meetings. It stands for subjective, which captures what the patients report, objective, which is what the doctors observed or measured, and then there's assessment, which is where the doctors analyze the situation, and finally plan, where the doctors outline the next steps, treatment, and medication that the patients must take. So in short, it provides a standardized way to document and track patient care across the healthcare team. Now, what we're exploring in this study is whether large language models can generate these SOAP notes automatically from a given meeting or from the doctor-patient dialogues. For this study, we experimented with fine-tuning several models, including T5, LED BART, and Phi 3.5 mini instruct. So let's go over our methodology. First, we start with our raw training data, which consisted of dialogues between doctors and patients, along with the corresponding SOAP notes from that conversation. Next, we applied prompt engineering to make sure the input format was consistent and clear for the models. After that, we tokenize it, and then we move it into the sec-to-sec model initialization, where we set up architectures such as T5, BART, and LED. Then we define the hyperparameters like the batch size and training epochs. And finally, once that is configured, we proceed with fine-tuning the models, where it will learn to map doctor-patient dialogues into structured SOAP notes. From there, the model should be able to generate a SOAP note from a given dialogue. So how do we obtain our raw training data? Now, for this project, our dataset was synthetically generated using ChatGPT-4, which is publicized in the internet. We created dialogues between doctors and patients, along with the corresponding SOAP notes from that conversation. This approach, we believe, allowed us to build a large dataset while also avoiding privacy issues that come with using real medical records. And in total, we generated about 10,000 samples, 9,000 of them which were used for training, 500 for validation, and 250 for testing. As for how our dataset looked like, there are two attributes. First is the dialogue, which is a string that consists of a dialogue between the patient and doctors, so their whole conversation. And then the SOAP note that corresponds to this dialogue. As for our evaluation method, we use the Rogue One, Blue, and Brit score. And on the right here, you can see the hyperparameter settings, which were chosen to balance both our computational capabilities with the model performance. Now let's move on to the results that we got. So we evaluated our four models and found that when looking at the Rogue metrics, we can see that the LED model achieved the highest score across the Rogue 1, Rogue 2, Rogue L, and Rogue L sum. It slightly outperformed BART and is significantly better compared to T5 small and 5 3.5. Now, similarly for the Blue and Brit score, LED again comes out on top with the highest Blue score and the strongest average precision, recall, and average F1, as you can see here. Well, it didn't really outperform BART by that much, but again, in summary, across all evaluation metrics, the LED model consistently performs the best among all the other models tested. Now, this demonstrates that LED is particularly effective at handling the summarization task, which is likely due to its ability to manage longer sequences efficiently. Now, to conclude, our experiments show that the LED model performs best as it has consistently outperformed all the other models across all evaluation metrics, and it is particularly effective in handling long sequences, which is very much crucial for processing our medical conversations. Now, most importantly, this result has real-world implications, as by automating the generation of SOAP notes, our system can significantly reduce the workload on the doctors, and it can ease their burden, and they can focus more on improving patient care. For our future work, there are two main directions that we want to explore. First, we plan to expand the model selection. In particular, we aim to integrate GPT-based and domain-specific large language models, which could further improve performance and adaptability within our domain, which is the medical domain. Second, we are looking into multilingual and speech-to-text integration. This would allow the system to handle conversations in multiple languages and also directly process the spoken dialogues from the doctor and patient straight away through a speech-to-text pipeline. We believe that by doing so, we move closer to building a more practical tool for real-world medical environments. That is it for our presentation. Thank you for listening. Let me know if you have any questions.